Hello and welcome back, everyone. Moving on to section 4.2, we're calling this section the parametric curves in the plane. We're going to discuss both plotting parametric curves as well as constructing them as the two subsections for today. So we're going to start out with plotting. And when we think about plotting, traditionally what we've always done in the past is we've kind of really plotted the collection of the points x and f of x, right? This was, x, and we call it x because this is on the x-axis usually. And f of x we should really imagine as being attached to the y-axis. Right, so often we would write something like y equals f of x. And what we actually are trying to emphasize when we say y equals f of x is a description of graphing the values for the function on the y-axis. So this y has kind of always been referring to the vertical direction every time you've seen it. We haven't really treated it that way sometimes, but that's what it's trying to refer to. And so I'm just going to go over one example. I think everybody who's watching already knows this, but one example of maybe how we would plot functions that are just x comma f of x as the plot, because it's going to set us up well to see what we mean by parametric functions and how to plot them later. So let's just consider this function I've got here, which happens to be a quintic meaning 5 or 5th degree polynomials. I've got 5 terms of x that I'm multiplying together here, and I've gone ahead and factored those, so it's quite clear to see that the zeros of this function are at 2, 1, 0, -1, and -2. The 6 is just there to make the function pretty when you plot it. So this is a function that we'd plot, and suppose maybe we didn't know where these zeros were and I hadn't actually factored it. The way we would actually try to plot it is, well, we would start with this thing that I've already kind of introduced, which is to define the y value of our points to actually be the output of this function, right? We could have technically defined the y value of our points to be whatever we wanted. It just turns out that the value of a function is a very useful thing to do. It almost feels like second nature to everybody because we've been doing it since probably Algebra 1. And then the second step, which you've also probably been doing since Algebra 1, is to choose many, many values of x, right? We're going to create a collection of points, x comma y, by evaluating the function at those points of x and pairing them with the value of x. So for example, in our case, let's maybe choose for this function here, let's choose the x values -3, -2.9, 2.8, 7, 6, 5, all the way up to 2.5, 2.6, 2.7, 2.8, 2.9, and 3. So really what I mean by those is I'm going from -3 out to +3, and I'm splitting this interval up into tenths. So these are, 1/10 jumps between each point that I've put on my real number line. What we can do is we can actually evaluate the function f at all of these points just by, well, doing what you've always done, plugging that specific number, -3, in for every case of x and seeing what we get out of it, right? We would do the same then for 2.9 and put a 2.9 in, 2.8, all the way up to +3. What we get out of this, if we actually plot those points, is the following graph, right? And then kind of what we would always do is, in our minds, we're smart enough to know that the real number line is a continuous line. It's not this discrete collection of points. And so in our minds, we would always kind of connect all these points with a somewhat smooth curve. And then we would say that the smooth curve connecting all the points is actually the plot we were looking for. And indeed, if we do draw the smooth curve and get a computer to plot this, we're going to get, something smooth. So that's what it means to plot, basically, and I think everybody knows this, but when we think about doing plots for parametric functions, which I'm going to talk about now, we're going to do them somewhat similarly where kind of we have a two-step process to plot. And this should be true whenever we plot. The first step in our two-step process is to choose a lot of values for the independent variable. And I know you've probably been introduced to this term independent variable multiple times and you've never quite decided to memorize it. Independent, we call it independent because we have that choice, right? The fact that we are able to choose at the beginning is why we call it independent. It doesn't depend on anything else that the world's giving us. We have free choice over it, okay? So independent variable is the one that you have choice over what values you want to use. And then the second step is to evaluate the function at those values from step 1. So this is always the process. We just saw it from before, but with parametric curves, things change. What we get out of this evaluation changes in parametric curves. So let me highlight that and say the evaluation doesn't look like points x comma f of x in parametric curves. Rather, it is x of t, y of t, where, and I should have really said this for step 1, t happens to be our independent variable. This is now our independent variable. But if we think about what that means for plotting, we're still plotting xy points, xy coordinates. You can see here we don't have a specific coordinate that just looks like t, right? You could imagine t and f of t as a common way to plot a function of t, but we're not going to do it that way anymore. We're actually going to plot, every time we plug a t in, we're getting two outputs in a parametric curve, and we're going to plot the two outputs, but not t itself. So that lets me get to actually defining these parametric curves. The way we define a parametric curve, and this is specific to the plane, you can actually have parametric curves in any number of dimensions. You can have them in 3 dimensions, 4 dimensions, and so on. So in the plane, we're thinking 2 dimensions. Planes are 2-dimensional objects. This is going to be a function, f, that inputs a time window. So this is really where it harkens back to dynamics this whole time. So the input to a function is a time window, but the output is actually a 2-dimensional point, R2, right? It's some point in R2. And so it's defined by, well, just f of t being your time variable, and then you get not 1, but 2 outputs. And you consider those 2 outputs as a point in the 2-dimensional plane. And in terms of plotting, we only plot the outputs. If I jump up to my earlier example, when we think about plots like this, we have the ability to plot the input here and the output here, right? We're lucky in the fact that when we just have something like x, f of x, our pieces of paper, our computer screens are 2-dimensional objects, and so there is only 2 dimensions that includes both the input and the output. When we're working with parametric curves, since the output is already 2-dimensional, we've used up all of our space, so we have to kind of give up on being able to plot the input. So we give up on plotting the input, and we only plot the output. A lot of times we don't write parametric curves as a function f anymore. It's much more common, where I say equivalently here, how we describe these is we just write out x, the x value of the output, as an expression of t, and the y value of the output as an expression of t. And so often we will just use 2 equations or 2 functions of t, where the first describes the x coordinate output, and the second describes the y coordinate output. So that's really what we should think with parametric curves. These are going to be some function for x and some function for y. Both are going to depend on a time window. So how do we actually plot this? Well, it's the same as I said before. Basically, if we're given this 2-dimensional output, an xt and a yt considered as a point in the xy plane, we produce a plot by choosing a large enough collection of values for, in particular, the variable t, right? We're going to choose the input variables within the range of their time window. And then we're going to obtain a collection of 2-dimensional points by actually evaluating each of our functions at those values from step 1. And then we're going to plot each of the points we ended up with in step 2. And then finally, we're going to do this idea of connecting the dots in order with some sort of smooth curve. And that's going to give us the plot of these parametric curves. So let's look at a nice example of what I'm calling an equilateral triangle. And this is going to start to kind of show the importance of parametric curves, because if we go back to our regular idea of plotting functions like x comma f of x, this can never be a triangle because that would fail the vertical line test. And the reason it fails the vertical line test is because we have the ability to plot the input. The reason why an equilateral triangle, when we're using parametric curves, doesn't fail the vertical line test is what it means to be a vertical line no longer makes sense in the 2-dimensional plane. You would actually have to extend to 3 dimensions to describe what this idea of a vertical line would mean. And so we can have kind of shapes in the plane that no longer satisfy the vertical line test, but are still nonetheless functions. And so we can start to do calculus with these objects. It's going to take us a little while to get to the calculus in this book, but we will see eventually we can do calculus with these objects, which is quite useful. And we don't have to worry about vertical line tests. Anyway, the equilateral triangle is going to look like, well, you can see what I've done here is I have in this case, a piecewise function for the x coordinate, and similarly for the y coordinate. So I have a piecewise function for both of those. Let's recall what piecewise means. It means if I put a number t in, maybe 1/2, for example, I have to check which one of these 3 situations is true. And so I check when t is equal to 1/2, which of the 3 cases is true. 1/2 happens to be in the interval 0 to 1, and so that's going to point me to the left and say I'm actually going to use this definition of my function. But if maybe I were equal to 2, I check and replace t with 2, and that satisfies this interval, so I would put a 2 into the bottom case. Okay, and it looks like our time window here, it looks like we start at 0 and we end at 3. So we're going to choose some values of t between 0 and 3. In this case, we're going to choose every 1/4 value between 0 and 3. And then we're going to plug them in and see what we get. So in step 2, I'm actually going to grab this 0, and I'm going to go ahead and plug it in for both of my points. I then, because they're piecewise, have to check which of these intervals is the true case, and in the case of 0, that's going to be the first one. So I'm going to plug a 0 in for that t, a 0 in for that t, and these are going to reduce to √3/2 and -1/2, or in terms of decimals, about 0.87, -0.5. So that's my xy coordinate corresponding to t equals 0. Then if I move on to t equals 1/4, I'm going to check which interval I'm in, which still happens to be the first one. Of course, I'm not going to transfer to the second one until I reach a t value of 1. So then I'm going to plug in 1/4 for this t, a 1/4 for this t, and that's my x value, that's my y value. In decimals, that's 0.65, -0.13. Let's jump ahead a little bit. Suppose I was plugging in 9/4 for t. I have to check which situation 9/4 is, which by the way is 2.25. That's going to end up being in this bottom case, right? Because 2.25 is between 2 and 3, which means if I plug in 9/4 here and 9/4 here, I'm going to be looking to 9/4 there and 9/4 there, but there's no 9/4, but there's no t to include there, and so it'll just be -1/2 for y. In terms of x, I would actually compute this out, and it looks like the x coordinate will be 9/4, about -0.43 and -0.5. Okay, so if I had done every single one of these t's, it turns out with parametric curves, computers can be our best friends. If I plug in all of these t's and actually look at the collection of xy coordinates I get, it's these 12 values. And if I go ahead and plot these 12 values, plot as x, y points in the plane, what do I get? Well, I get the collection of points you see here. And in fact, if I went ahead and connected the dots in the order that they show up, I end up with exactly the equilateral triangle we're talking about. And so this truly is the plot of the parametric curve, which is constructed by these two functions. And we'll eventually be able to do calculus with these sorts of objects, which I'm very excited about. The next example, I started off with a pretty easy example. The next one's just to get everybody excited. The calculations are going to be particularly tough. We're going to need a lot of points to really see how to plot this. So once again, computers are going to be your best friend. But we're going to talk about the spirograph. And I don't know if this is a generational thing and maybe you didn't grow up with them, but the spirograph was really this toy which consisted of like a large gear, and it was really a stencil. So it was some giant gear that was open on the inside, made of plastic, and then you would place a smaller gear inside of the larger gear, and the smaller gear would have multiple little holes in it that you could put your pencil inside of. And what you would do with the spirograph is you would grab your pencil, put it inside that hole, and you would roll the inside gear around the outside gear, and it would create some sort of, let's see if I can do the best I can here, create some sort of like shape as it rolls around that would do something like this as the inside gear rolls around the outside gear. And these were called spirographs. You can still look them up if you want to. Mathematically, these are given the name hypocycloid. A cycloid is any case where you have one wheel rolling on another surface. Hypo in this case meaning we've put one circle inside of another, or really one circle smaller than another circle. So we do call these hypocycloids for curves, but you can construct them parametrically, really quite straightforward, just as kind of a sum of sines and cosines in my x and y coordinate, where in particular what's important here is that we've got a different radius is how you can think about this. The multiplier, the coefficient of one of the sines and cosines, than the second multiplier. And as well, you have a different frequency, right? We've got the first frequency should always be 1, but these later frequencies should be some higher frequency. So you can play around with these objects. If you want to change the numbers around, you just want kind of a smaller radius on the high frequency term. That makes sense, right? Because this smaller circle, which has a smaller radius, is going to have a higher frequency because it's going to be spinning around more times than the single large circle. So this is what the hypocycloid is going to look like. Let's actually go ahead and plot it. And to plot it, we're going to do the same thing we did before. So I've gone ahead and chosen the 1/24th demarcations of the unit circle here. I'm not going to go through evaluating all of these, obviously, in the video at least, but I will go through kind of how I did a couple of them. For example, maybe pi over 6. I'm going to go ahead and plug in pi over 6 here, 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 and pi over 6 here. And what we end up with is, in decimal, 0.89, 0.42. Or for example, if I chose 19 pi over 12, I would put in a 19 pi over 12 here, 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 and 19 pi over 12 here. And where would that be if I actually evaluated it? Well, you end up with 0.05 and negative 0.8. So if I go through all 24 of these points and I decide to plot them, we get the following collection of points. In fact, if I go ahead and connect the dots in the order that they were plotted, I end up with the following, which does not look correct. So if you're ever plotting parametric curves, and it's hard to see the pattern, there's unfortunately exactly one thing you have to do. You need to choose more points, which is a lot of work. This is why we rely on computers and calculators to do this for us. But in our case, I've gone ahead and chosen 100 points instead. And at 100 points, it does get a little bit nicer. You can start to see this pattern show up, where if we connect these dots in the order they came, we end up with this. And I've gone ahead and had the computer connect the dots with straight lines first, then with smooth lines second, and we really can see that spirograph. It's very cool between both the equilateral triangle and our spirograph case to imagine that, we couldn't really plot functions that looked like this before. So parametric curves are really special in that they can plot these more abstract functions, and eventually we are going to see that we can do calculus with these functions. But the second half of today's work is actually not going to be on plotting anymore. It's going to be almost the reverse. Somebody's going to come to us and they say, hey, I would like a parametric set of equations that describes some particular shape that I have in mind. Like maybe somebody has a smiley face in mind, and you could construct a set of parametric curves that actually constructs the smiley face. Or maybe they want to see a pentagon, for example, or maybe they want to see a line that goes back and forth, and then it kind of gets bigger and it comes back and it looks a little bit like a snake, right? You can do all of these with parametric curves. Moreover, you can actually do calculus with them eventually. So we're going to be able to calculate areas of these, for example, by the end of the book. It's a long ways out to do the calculus, but we will be able to do that eventually. So the question becomes, how would we actually go about defining a set of parametric curves that can give us those shapes? And primarily the way that we're going to learn how to construct these shapes is by learning a very, very small collection of shapes first, namely lines, ellipses, and what we're used to with functions of x and y. And then we'll kind of try to synthesize those if we have to into whatever function somebody's asking us to synthesize them. So in the first case, which is lines, or also known as line segments maybe, segments between 2 points, how we're going to construct these is we're going to look at our points, and suppose we start with 2 points, x min, y min, and x max, y max, and give me a nice example here maybe is the point x min, y min, and then maybe I want to connect that to a new point, x max, y max. Just because I say min and max, I don't mean that the y value at y max is larger than y min. I kind of mean to say that since we're connecting these temporally, we should think about the parametric curve as a collection of points which evolve over time. We have a t min, we're going to end up at the first point, and some later time, t max, we will end up at the last point. So that's why I use the min and max to refer to these points. And so suppose we want to connect those over some time window, t min to t max, and that's actually, the time window is often up to us to decide. We can make that choice ourselves. But there are often useful time windows, like 0 to 1 is very useful, 0 to 2 pi, if we're talking about going around a circle, is very useful. Going back to the equilateral triangle we talked about earlier, that really was just 3 line segments connected to each other. I decided on the vertices of the equilateral triangle, but I connected all of them with line segments. A very natural t min, t max was 0, 1 for the first segment, and then 1 to 2 for the second segment, and maybe 2 to 3 for the third segment. So I made that choice for myself when I constructed them. And so let's talk about how we would use these 2 points, as well as maybe our time window, to actually construct parametric functions for both x and y. The way it's going to work is we're just going to grab directly out of my points. I'm going to take x min, and it's going to end up in 2 places. It's going to end up there and there. I'm going to take x max, it's going to end up right here in one spot. I can take y min, that's going to end up in 2 places, here and here. And I can take y max, and that's going to end up right there, as well as my t min, which will end up here and here, here and here, as well as t max, which will end up here and here. So I'm just going to grab each of those 6 terms that I've kind of decided on for my parametric line segment to exist with, and then I'm going to input each of them into that expression for x and y. So look at an actual example what I have over here, maybe I want to connect negative 1, 1, which I'll put right there, negative 1, comma 1, connect it to 2, 3, maybe that's up here, 2, comma 3, and so I want to connect them with this line. How could I do that? Well, I just have to identify all my pieces and put them in the right spot. So this is x min, for example, and x min ends up here and here, so I'm going to put a negative 1 in there and there. This is x max, for example, x max is there, so I'm going to put a 2 right there. My time window I have from a 3 to a 5, and in this case, imagine that somebody handed that to me, even though I could decide it for myself. Tmin is here and here, so I'll have a 3 here and here, and the Tmax is there, so I'll have a 5 there. And in terms of y's, if I look at ymin, that's going to be a 1 in this case, so ymin will end up there and there. I have a 1 and a 1. My ymax is a 3, and so I look and find ymax up here, so I'll have a 3 right here. And then just as before, my interval was 3 to 5, so I'm going to look at 3, 3, and 5, so I'll have a 3, 3, and a 5. Now I could be satisfied with this collection of parametric curves, but of course, 2 minus negative 1 is 3, 5 minus 3 is 2, so really there's a 3 halves there. 3 minus 1 is 2, and 5 minus 3 is 2, so those will cancel. And I'll just have a 1 there, so here's where I have my 3 halves and my 1. And so that's going to be my collection of parametric curves, which describes this particular line segment I'm interested in. If I go ahead and plot it kind of the way we were doing in subsection 1, we see, yes, I've plotted that line segment correctly. Okay, we can also talk about ellipses, parametric ellipses, and what we're going to do for parametric ellipses is define a center for the ellipse, as well as an x radius and a y radius. And I'm going to talk about what each of those terms are now. So suppose I have an ellipse here. The center is, of course, fairly self-explanatory. What does that mean? It's just the point in the xy plane that I'm going to center the ellipse at. But the x radius, because it's an ellipse, kind of the distance out in the x direction will have a different radius than the distance out in the y direction, right? The point of an ellipse is that these two distances are going to be different, or possibly could be different. And then I also have the ability to choose the time window here as well. That'll just be up to me. And let's talk about where these equations actually come from. Well, I've got an x0 and a y0 here. That's just going to be my center point because it's going to shift kind of the x and the y outputs to those points to start with. And then how do I actually draw the ellipse? Well, if we think back to the unit circle, the x-coordinate on the unit circle depended on the cosine of the angle of the unit circle. And so I'll have a cosine from the x component, and the angle is really going to be this entire term 2 pi as well as this junk with t. But where's this junk with t coming from? That junk is really normalizing t into the window, the new time window, 0 to 1. Okay, it was doing that in the case of the line segment as well. You can kind of like renormalize the line segment to say, oh, I'm just going to start at where I start and end at where I end after 1 second or whatever. But to normalize an arbitrary time window into that 0, 1 time window, this is kind of the price you pay. You just subtract the minimum time and then divide by the total length of the time interval. So the reason why that modifies to 0, 1, and then I've got a 2 pi here is because we make 1 full revolution after 2 pi radians, not after 1 radian. And then finally, the Rx that's out front is just exactly referring to the Rx. It's going to scale the x direction by this particular radius. And then we're going to do the same thing with Ry. The only difference is that because of the unit circle, it's the sine of the angle defines the y value, not the cosine of the angle. So that's where the equation of the ellipse actually comes from. And in particular, we can also construct a circle, kind of the most generic circle. Circles are the case when these radii are the exact same number, right? An ellipse with a left, right, and up, down equal radius will be a circle. And so we're just going to have a single number for the radius there. Suppose I want the circle centered at the origin, kind of the classic circle. It's just going to be x is r cosine t, y is r sine t, and t is just going to evolve around the circle, so from 0 to 2 pi. It's kind of my favorite one to refer to if we're ever going to construct a circle will be this collection of parametric curves. As an example of an ellipse, suppose maybe I want to construct an ellipse centered at -2, -1, with an x radius of 3 and a y radius of 2 over the time window 1 to 3. How could I actually do that? Well, let's just refer back to my equations. My center, the x component is -2, so I'm going to plug in a -2 for x0. The y component is -1, so I'm going to plug -1 in for y0. The x radius is 3, so I'm going to plug a 3 in for the x radius. The y radius is 2, so I'm going to plug a 2 in for the y radius. And the time interval is 1 to 3, and so t min will be 1 here, 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 and here. There's my 1, 1, 1, and 1, and a 3 here, here, and a 3 here, and here. So once I have all those, I can actually simplify it just a little bit. Ends up being this collection of equations, which if I go ahead and plot using the techniques from the first section, I'll end up with the exact ellipse I was looking for. So there's a little bit of verification that these equations work. And then the final example is a pretty cool example. We can actually plot like our favorite regular plotting functions like x comma f of x from algebra 1 and everything else we know in terms of parametric curves. So suppose we want to include periodically the calculus we know and love with x comma f of x. We can do that with parametric equations just by defining the set of parametric curves. X of t is t and y of t is f of t. Now why does this work? Well, if I've just defined that x is equal to t, and y is equal to f of t, well, you can imagine because x is t, I can go up here, and t and x are the same, so we're going to replace that x with a t, and that's taking up the place of the y component anyway, and so t f of t and x f of x are of course going to create the same plot here. Now my time window does have to be over whatever interval the original x interval was, right? If I care about a very specific x interval in the original plot, the t interval in my parametric plot should be the same. You can kind of do the same when it comes to functions of y as well. We didn't do this as often, you know, in our algebra courses or pre-calculus courses where we would plot something like a function of y against y, but I think periodically did, right? You would maybe do the parabola on its side every now and then. This would be something like x equals y squared. Was maybe something you'd get used to, and you'd say, oh no, that doesn't pass the vertical line test. But we're not actually talking about the vertical line test. If you think about x equals y squared, we're now talking about the horizontal line test, because we've described functions in a different axis. So we described them around the y-axis as our independent variable instead of x-axis as an independent variable. But anyway, we have the ability to graph these as well, the plots g of y comma y, doing the opposite of what we did before. So we're just going to define y to be equal to t and x to be equal to g of t. And so we can do functions of either x or y parametrically. And here's maybe an example. If we want to plot the function x squared minus 2x minus 1, now we can, of course, we can do this just with our xy plane as we've always done, but we're just going to try to get used to doing it parametrically, because maybe we want to connect these with some other parametric curves like circles or line segments or ellipses or something in the future. What we do is we define, okay, x is just equal to t, and then we go ahead and look back at our function and say, oh, by the way, if x is equal to t, then x is actually equal to t and t, and so this ends up being the function for y. And then we exactly grab the x interval in the original function to become the t interval in our new parametric curve. You can see if I compare plotting like we used to, you know, this is x comma f of x as the plot that we're used to. This is actually x of t comma y of t. So this is parametric plotting on the right, but you actually end up with the exact same image. And then the same example, if we want to do this in the variable y instead, y squared minus 2y minus 1, if I wanted to plot that, well, we're just going to let y equal t. And because we've let y equal t, that means this y is actually equal to t, and this y is actually equal to t. And so that ends up being our function for x. And the time window comes straight out of the window for y. And what do these plots look like? Well, it's like I was saying before, it's kind of this horizontal parabola instead of a vertical parabola, but we interpret the left hand as g of y comma y, we interpret the right hand as x of t comma y of t. So it's a parametric plot on the right, even though they look the same. That's useful because we want to be able to do kind of our classical calculus along with this new modified calculus eventually. Okay, so then what I say is between the previous three examples, so we saw line segments, ellipses, and functions of x and or y, we're going to try to synthesize these and perhaps combine multiple cases to construct specific parametric curves maybe somebody asks us for. So this first example I have is a case of a rounded rectangle, and it's the art department that has asked us to construct this rectangle. And what they need it for is a couple stencils that they're going to be cutting out with a vinyl cutter. Okay, so they want the parametric equations which describe really what their vinyl cutter should cut, and it's going to be, what is this shape? We've got a line segment from between 2 points, and then a semicircle, and then another line segment, and then another semicircle. So we're going to have to construct the parametric curves for each of these pieces and kind of stitch them together. Now the art department has done a nice job and told us kind of what these special points are on the four corners of our rectangle. They're negative 3, 1, 3, 1, 3, negative 1, and negative 3, negative 1. So we have some sort of idea of the line segments we should be constructing. So how are we going to actually construct this? Well, we have to make a choice about where we're going to start. And then we also need to choose time windows for each piece. In this case, I'm going to choose to start right here, and I have a very good reason for doing that. My reason is that if I start there and I move to the left, then I can rotate around a circle in a counterclockwise fashion, which is the way we normally plot circles in math. So it's not going to make my life any harder to move in the counterclockwise direction. I wouldn't want to accidentally go in the clockwise direction. And let's say I want to traverse that semicircle over the time window 0 to 1. This is completely up to me. And then let's say I want to perform the next line segment over the time window 1 to 2. And then let's say I want to do the next semicircle over the time window 2 to 3. And then maybe I want to do the very last line segment over the time window 3 to 4. So I'm going to have to construct each of these kind of portions of a parametric curve over their respective time windows and then stitch everything together at the end. So let's just focus on that left semicircle here. And so what I have here is saying that we can construct a left semicircle over this time window by understanding that, well, what does it look like? It's got a radius of 1, because this was at the point, what, -3, 1. So that's a distance of 1 from 0, and then this was the point -3, -1, right? So even though the diameter is 2, the radius is 1. And the center happens to be, what is that point between those two? The midpoint is -3, 0. Okay, so I know my center and I know my radius, and that should be enough, along with the equation of a circle, to give me what I need, right? So here's my collection of terms from the equation of the circle. In particular, if I look at x0, there's x0, y0, y0. My radius of 1 shows up as the coefficients here and here, and my time window 0 and 1 shows up as 0 for t min and 1 for t max. So I've taken that straight out of me knowing how to define an ellipse using parametric curves. Okay, so that should be pretty good, right? Except these equations construct the entire circle, right? If I actually drew these out, what would I get? Well, I definitely have the correct center, 3, 0, but what would happen with my equations is I would start over here and I would traverse an entire circle in the counterclockwise fashion rather than the semicircle that I'm actually looking for. So what am I really going to try to do here is I need to break this circle, and I only want the left side of the circle that I just drew. So how do I actually get there? In the first case with the 2 pi here, that took me all the way around the circle. I only want a semicircle, so I want to have the speed of this circle, which means I'm going to replace t with t over 2. And just having the amount of time that I'm spending there on the circle. So that's going to reduce me from a full circle to a semicircle. But if I just reduced it by half right away, I would get the upper half semicircle, because these circles always start on the right. That's how the unit circle works, and that's how cosine works. It would start me on the right. I don't want to start on the right. I want to start at the top, and that is exactly a pi over 2 rotation. And so I have to go extra and include a pi over 2 rotation, which means I get to add pi over 2 to both sine and cosine in my equations. And so this is actually going to be the set of equations that's going to construct a semicircle for me. The t over 2, by the way, I did include it, but then canceled with the 2 pi, so that's why I just have a pi here and a pi here. This is going to be my collection of equations, and if I go through the work to plot, we do indeed see the semicircle show up, so that's great. I can feel good about myself again. The next segment is going to be this line segment. Well, what are the points? This is the point -3, -1, and it's going to go out to the point 3, -1. And if I use those 2 points in the line segment example, well, x min is going to be -3, there it is, and there it is. X max is 3, there it is. Y min is -1, there it is, there it is. Y max is -1, there it is. And then the time window ends up being 1 to 2, because it's the second section I've traversed. So t min is 1 and t max is 2. And if I go ahead and simplify this line segment, I get the following equations for x and y, and I can verify by adding that to the plot, and indeed I've got that line segment correct. Now I get to focus on the next semicircle, which makes its way up from 3, -1 to 3, 1. And I'm going to do this the same way I did before by identifying the midpoint. Well, the midpoint or the center being 3, 0, and the radius here, the radius is equal to 1 yet again. And so that circle, if my midpoint is 3, 0 with radius 1, looks like, well, 3, 0, my radius is the coefficient on cosine and sine, still a 1. My time interval is going to be from 2 to 3, because this is the third section I'm building. So t min is 2 and t max is 3. But just like before, what would this collection of equations actually construct? It would construct an entire circle centered at the point, and it would start the circle here. And instead, I need to start the circle down here. So I need a -pi over 2 rotation, and I only need the semicircle, and so I'm going to take t and I'm going to divide it by 2. If I go through the work of this -pi over 2 rotation as well as dividing t by 2, what do I actually end up with? Well, here's me dividing by 2 for t. That's still going to cancel with the 2 on the pi. And then here's me rotating by -pi over 2. And if we go ahead and plot this third section of my parametric curve, we're getting really close. We just have one more line segment to construct between 3, 1 and -3, 1. Well, how am I going to construct the line segment between those points? We can identify 3 as x min, so it's there and there. -3 is x max, so it's there. We have 1 as y min, so it's there and there. We have 1 as y max, so it's there, as well as the time interval 3 to 4, so I have 3 for t min and 4 for t max. If I simplify that section, I end up with this collection of a parametric curve. And if I add that to my plot, we can see I have indeed ended up with what I'm looking for. So how do I combine all 4 of these steps together? Well, I'm just going to use a piecewise function, and I'm going to include this definition over the piecewise term t in 0, 1. I'm going to include this definition over the piecewise term t in 1 to 2. This definition over the time window t in 2 to 3, and finally I'm going to include this definition over the piecewise time interval t, and 3 to 4. If I combine all those definitions, specifically for x, I see that x has its 4 components. 2 of them look like circles, the other 2 look like lines. And y has its 4 components. 2 of them look like circles, and 2 of them look like lines. So this is my collection of parametric curves that will construct this, kind of pill shape boundary. Finally, I do have to include this very last example because every single calculus book includes it when you talk about parametric curves. This is called the cycloid. Remember I called the spirograph the hypocycloid earlier? This cycloid is a shape that's going to be constructed from marking a point on the edge of a wheel and then tracing the point through space as the wheel rolls. I have a nice diagram of that here. My wheel has showed up on the left, and I'm going to rotate this wheel to the right, you can imagine, as it rotates, and I look at one specific tracing point on the wheel. As it rotates, the wheel is eventually going to end up kind of over here, and my tracing point will be right there, and I can continue maybe later. My wheel is going to end up right here, and my tracing point will be right there just before it touches down again. And as I just continue moving the wheel to the right, it traces out the path you see here. So this path is called a cycloid. We're going to try to construct it using our knowledge of parametric curves. So how could we construct it? Well, we're going to construct this in pieces. Let's imagine that we have a fixed axle, meaning that I'm not actually going to move the wheel to the right. So let's say no motion right. And I'm just going to I pick my wheel up from the ground and spin it in place. What's going to happen to this tracing point? Well, it's going to spin in this direction, right? The tracing point just moves around the wheel. Imagine if I don't move the wheel to the right at all, it just kind of makes its way around that wheel. Well, what is that? That is a clockwise circle, centered at the point 0, 1 with radius 1. Okay, so that's a lot of information, right? Radius 1, centered at 0, 1. Clockwise is the negative direction that I'm used to. And what else do I need to know about this? At t0, so at t0 where I start at the bottom. And the bottom in this case will be the point 0, 0. Okay, so a mixture of all of that information. I'm going to try to construct the parametric equations for a circle, which evolves clockwise, centered at 0, 1 with radius 1, and a starting point of the origin 0, 0. So how am I going to do that? Well, the center 0, 1 is pretty easy. I have a 0 for my x-coordinate, 1 for my y-coordinate. Radius 1 is easy. That's just a coefficient of 1 and cosine and sine. But to get it to be clockwise, I'm going to have to replace a t with a minus t. And to get it to end up so that this is my starting point at the bottom, well, what do I have to do is I have to move exactly a negative pi over 2 rotation, right? That's a negative pi over 2 rotation. So I'm going to include a negative pi over 2 rotation on both the cosine and sine terms, as well as a minus t to get the clockwise into place. That would be the motion around the wheel alone without it moving to the right. Now when we think about the wheel, the center of the wheel moves to the right. And we need to know how fast it moves to the right to actually construct this. Well, how fast does it move to the right? We know that after one full rotation, t has moved from 0 to 1, right? At least the case in the case that we've drawn this, because we've given ourselves a 2 pi right here. So one full rotation, t starts at 0 and it ends at 1. Well, how far has it moved on the ground after one rotation? Well, if I'm tracing on the ground one entire circumference, one rotation is one circumference, that means that this must be one circumference, which a circumference of a circle of radius 1, 2 pi r, when r is 1, will just be 2 pi. This has occurred over a time window 0 to 1. I know that I'm moving exactly at a speed of 2 pi, or 2 pi divided by 1. And so my speed is going to be in the x direction because I'm moving to the right at a speed of 2 pi. And what is the value of the center? If I'm just talking about the center of the wheel, how does the center move to the right? Well, it's this 2 pi t. What is its y value? The y value is always going to be equal to 1. So the center of the wheel operates under its own set of parametric equations, 2 pi t and 1. And now if we want to combine the two things we've come up with, the wheel itself, the point around the wheel, just rotates around a circle given by the following, but then the center of that circle is no longer 0, 1. The center of the circle moves to the right. The center of the circle moves as 2 pi t, comma 1. And so if I combine all together, I'm going to put the center of the circle into my circle equation that I've already constructed, and now I get a 2 pi t, 1 for the center, and this is the point revolving around the wheel. So this is the center moving right, and this is the point rotating around the wheel. So this will actually be my collection of parametric equations for this cycloid derived from scratch. And if I want to simplify it, I can. I won't go through the simplification, but you can see it on the board here. We simplify it to these equations, actually, just a couple trig identities used there. If I go ahead and plot these as a collection of parametric equations using my knowledge from the first part of today, we do get exactly the cycloid curve that we had before. And so we can verify that what we did was correct. Anyway, that's all I've got for today. We're going to move on to polar curves in the next section. So if you remember all the way back to the start of the semester when we talked about polar complex numbers, we're going to do that with curves as well. So I'm looking forward to that. I'll see you in that section. Bye.